Okay, so here is today's offering, equilibrium condition and the equilibrium constant. All right, I want to talk about first what the equilibrium state is. It's a mixture of reactants and products whose concentrations no longer change with time. And in order to understand that more fully, you need to know this, that every single reaction is reversible. Up till this point, I've written your reactions as the reactants become products. Well, in actuality, in a closed container, once this product starts building up, there's an impetus for the product to go back and become the reactant. It's a reversible exchange.
So
All reactions that are carried out in a closed vessel will at some time attain equilibrium. That's when the reactants are becoming products and the products are becoming reactants. The definition of equilibrium is when the rate of the forward reaction is exactly equal to the rate of the reverse reaction. So if we would take this general thing, when it reaches equilibrium, the rate of the forward would be Kr, is exactly equal to the rate of the reverse, Kp. Now, it would seem to the casual observer that the reaction has stopped. If there was if you just thought about it, hey, I think this thing is done, it's at equilibrium, there's no more change in the ratios of reactants and products. They're still moving. This is a dynamic state. Someone will try to fool you with a question that says, at equilibrium, the forward and reverse reactions stop. They're just moving at the same rate of speed. Yes?
So there'd never be a reaction where the energy needed to start it would be available for one reaction, not the other? Like the activation energy would be too high in the reverse direction, so it wouldn't be able to?
Nope. Nope, because they're going to be inverse. Right. So if one was high, the other was low.
So like if you're making an alloy, like for example bronze, and like you mixed your
You know what? I think mixture is not.
Oh, it is?
Yeah,
That's
a
lame.
mixture is not a chemical reaction.
but
Okay.
it forms bronze.
Alright, so, what happens when equilibrium occurs, the rates are equal, forward and reverse. This keeps the ratio of the concentrations of reactants and products equal. The way you write an equilibrium reaction is with a two-headed arrow. This denotes that a reaction has reached equilibrium. Right, here is my favorite reaction of all time. A plus B is in equilibrium with C plus D. By definition, that means the rate of the forward reaction is equal to the rate of the reverse reaction. So let's look at this as time goes by. Where's my color? Here we go. There we go. So we start out at time equals 0 with only our reactants. All of our reactants present, no product is present. So time passes, the concentration of the reactants decrease, while the concentration of the products increase until such time as equilibrium is established. And equilibrium depends on a number of things. But once equilibrium is established, the concentrations, the ratio of the concentrations of products over reactants does not change. Good? Of course you're good. Okay. Now let's talk about the equilibrium position. Let's say we started out with 10 molar A, 10 molar B, and no C and D. We put them into a closed container and allowed it to come to equilibrium. So first we started that, notice it's a single-headed arrow. At equilibrium, we measured the concentration, and we noticed that we have 9.5 molar reactants and 0.5 molar products. This means that very little of the reactants became products. When that happens, very little product is formed, we say the equilibrium lies to the left, or another expression is the equilibrium favors
Reactant.
the reactants.
I have another question that isn't about alloys. So, like, if you had a suspension or whatever those things are called in,
How do you
Yeah.
get a suspension?
When it's saying to the left, is that to the left of where the equilibrium point would be on the
No,
right?
no. What it's saying is that equilibrium favors, that means that more of this is around than this is around. The ratio, yeah, the ratio means that there are more of this than there was of that. Yep. Okay. Now, if on the other hand we start out with the same 10 molar A and B and had 0 C and D at the start of our reaction, we let it come to equilibrium, and we notice that almost all of the reactants were used up and it became product. We say equilibrium lies to the right, or equilibrium favors the product. Favors, stop it. All right, whether the reaction lies far to the right or far to the left depends on 3 main factors. Initial concentrations, I don't believe that. The relative energies of reactants and products. Let us recall that the universe is
relative.
lazy. And the universe will favor anything that is a low energy state. So there you go. And the degree of organization of the reactants and the products, nature also likes to favor those with maximum entropy. Remember that? Okay. Let's talk about the significance of K. What is K? Yep, the equilibrium constant. All right, now I want you to know it's a large K. What is a small k? Rate constant. Really? All of those symbols and letters in the world, and we are going for K. I don't know what the deal is there, but anyway. All right. If K is a number greater than 1, that means the reaction favors the product, or it is right at equilibrium. If it's less than 1, it favors the reactants.
And so this would be a different value than the rate constant?
Absolutely, absolutely. What does K equal 1?
They're exactly
They're
the
the
same.
same.
The
Equilibrium.
concentration is the
Yeah,
same.
equal.
Equal equilibrium, exactly so. I don't know how you'd get that to happen, but equal equilibrium. Neither one is favored. Oh. All right. Now, we're going to use the equilibrium constant to write an equilibrium expression. The equilibrium expression is a general description of the conditions of equilibrium. All right, there's another thing about chemists. If we can use one word or term to describe something, we're unhappy. We need multiples that mean the same thing that are only there to confuse you. I would very much hate to see you lose points on the AP exam because someone asked you to use the law of mass action and you're like, I have never heard of that in my entire life. I hate my chemistry teacher. Because this is the same thing as the equilibrium expression. It's the same thing as using the equilibrium constant. Now, this law of mass action is temperature dependent. It does change when the temperature changes. And therefore, all equilibrium expressions must tell you at what temperature this is happening. Must tell you at what. All right, the law of mass action, K, the equilibrium constant, the equilibrium expression, is not dependent on concentration or pressure. It's not dependent on concentration because it's a ratio, and the ratio won't change. Likewise, it's not dependent on pressure because it would, the pressure would affect everything, as you will see in a moment. So, if you had this reaction, took reactants A and B, and they were in equilibrium with C and D, and the little letters were the coefficients, the equilibrium constant for the forward reaction would be this. The products, where the coefficients are the exponents, divided by the reactants, where the coefficients are the exponents. So the law of mass action, the concentration of the products raised to the coefficient over the concentration of the reactants raised to their coefficient.
I thought it wasn't dependent on concentration.
So it would be the coefficient.
These are the concentrations at equilibrium. This is the ratio that we were looking at in that graph. What?
And that's the law of mass action.
That's the law of mass action, that's the equilibrium expression, that's the K is the rate constant. All those things are pretty much
Then
similar.
how is it not dependent on concentration?
The ratio is fixed.
The coefficient would be from the overall reaction.
From the balanced equation. Okay, here we go. This indicates molarity. So if you see the brackets, you know that we're talking about the concentrations at equilibrium. That is hugely, really giantly important. You are not allowed to put any number in here that isn't an equilibrium concentration. Do you understand? When you go back at this graph, none of these concentrations can be in the law of mass action. An infinite number of these concentrations can be in the law of mass action. Are you good there?
Would they be like changing, or would it just be a completely straight line? Like, would it be going back and forth just slightly, infinitely? Like, at one point you have a bit more of one than the other, and then you have a bit more of
Oh,
the
that
other.
is an excellent question. Stay tuned for 2 days.
I'll set a reminder on my phone.
Okay,
Just
okay.
lost.
All right. Now, here's the good news about K, the big K, that kind of drove you nuts with the little k. There are no units that need be written for K. There are units.
Yes.
And there's some really wicked thermodynamics that go behind this unit, but it's so far beyond the scope of our class, even Chem 1 and 2 in college, that we don't mess with it. Yay! So K, just throw the number out there. All right. These are the equilibriums that we will be studying for the next little while. KEQ is called general equilibrium, and a lot of times we just write it K. The EQ is dropped because chemists are lazy. KC is when you're talking about aqueous. KP is for partial pressure, and here's what's different. If we were looking at the KP, let's say all of these are gases for this reaction, K would be written like this. Why? Because
Concentration.
this is concentration, and if we're talking about partial pressures, these parentheses are denoting that we're talking about pressure, generally in ATM.
Would it have to be an 18?
Okay. KA is an entire chapter 14. KB, chapter 14 coming up next. KW goes along with this. And KSP is the equilibrium constant for solubility rules. This determines all your solubility rules. Okay. All right. Let's say that I determined that K for this reaction is 4,500. Tell me what that means.
It favors the product.
When you do C to the C power, D to the D power over A to the A power, B to the C power, it equals 4,500.
Yes, it does. Which is higher equilibrium concentrations, the product or the reactants? The products. Quite a bit, yeah? Okay. So if you were to shrinky dink yourself down, jump into the beaker, you'd see lots of this, and you'd see not a lot of that.
If it was that high, then now people think we need to shrink ourselves. 'Cause, like,
Well, I don't know. Yes, you would. Okay. So that's for the forward reaction. What if I want to know what the K value is, the equilibrium constant for the reverse reaction where C and D combine to make A and B?
we write it the other way.
It would be exactly correct. It would be the inverse. So the equilibrium constant for the reverse reaction is just the inverse of the forward. So if the reverse is equal to the inverse of the forward. Okay, got it.
Is that a little K on the bottom?
Nope.
No?
All right, whatever you do to the coefficients, you do to the exponents, get it? So from this reaction to this reaction, I multiplied by 2, multiply each one of the coefficients by 2. Not difficult to see there. Okay, if you have a set of elementary reactions and you would like to know what the K is for the overall reaction, multiply the K's for the baby steps.
Couldn't you just add them together, get the overall reaction, and then find the K with that?
No. No, you're not given that. All you have are the K's for the baby steps.
Oh, if we're
And you
given
want,
the-
yeah.
Okay.
Okay.
So it's kind of like this is except easier.
Yep. Okay, now there are two types of equilibrium, heterogeneous and homogeneous. Heterogeneous is when the reactant and products are not all in the same phase. Homogeneous is when the reactants and the products are in the same phase. Here's something that will trip you up, so pay attention to this. Pure solids and pure liquids do not appear in the equilibrium expression. Here is a pure solid. Leave it out. Water is the pure liquid that we most likely encounter. The reason that they're left out is one surmises that their concentration remains the same.
What other pure liquids are there other than water?
Milk.
Which is a mixture. Okay, only gases.
What about mixed nuts?
Only gases and aqueous ions appear in the equilibrium expression. Yeah, I guess, yeah.
Benzene maybe?
Yep. Yep. Okay, so here we go. Write the equilibrium expression for the following reaction. Step 1, check states of matter. Step 2, products on top. Step 3, coefficients become exponents. Step 4, reactants on bottom.
Repeat step 3.
Kind of. Step 5, repeat step 3.
Step 6. Right.
Okay. Gonna follow my own rules. Gas, 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 gas. So everyone plays. K
So this would be
is equal
KP.
to, no,
No?
nope. Because we could have concentrations of all of these.
But it'd be mixture.
Yeah. KEQ, or K, would be NO2 raised to the 4th power. Water's included because it's in the gaseous state, raised to the 6th power, over NH3 times O2, raised to the 7th power.
So just because they're gases, it doesn't necessarily mean we're using the partial pressure law?
Mm-mm.
As long as we're getting concentrations, really?
Because you will get molarity. Because remember, gas has volume, so, and you can count the number of moles, therefore you can have a molarity. Okay, moving on. In the interest of time and the fact that I'm,
Lazy.
did you say crazy?
I said lazy.
Now I'm not quite sure which one I like best.
I was making a joke on the whole chemists are lazy.
Okay, okay.
Oh, wait.
Good save.
Yeah, was that
Yeah.
That's what you're saying.
Yeah.
Crazy.
When mixed,
Woo!
mixed
Crazy.
on their own.
Insane.
Gas and mixed, can they just react on their own?
Sometimes if it's spontaneous.
This video is not
That's for another day. The decomposition of solid phosphorus pentachloride to liquid phosphorus trichloride and chlorine gas. Write K, which is KEQ, and P for the following. Okay, first you need to start with A. Thank you, balanced equation. Phosphorus pentachloride, which is a solid, turns into liquid
You sure
phosphorus.
yeah.
Phosphorus, well, I don't see you writing nothing. Phosphorus trichloride, which is a liquid, and chlorine gas.
So we have to do
So-
this.
No, no, yes. KEQ is dependent only on the chlorine gas. Notice that was balanced, by the way.
Wait, why is it only?
Because it's only the only one that's in the gaseous state. The equilibrium concentration.
Oh, for the KP?
Well, for all, both.
What's
KEQ
that?
Well, how do you know that
and-
it's a pure
Why
solid?
does it only depend on the one we have?
What?
Why would it only depend on minus and gas?
Because that was what I just said in the last page. The concentration in a closed container of the solid and the liquid aren't really gonna change.
So any
They're
solids or
considered
liquids?
constant. What?
Any solid.
Any pure solid.
How do you tell a pure
and
solid?
pure liquid. This is what I
that
want
better?
you to see the difference between this and, let's say, these are both liquids, yeah? This is a solution, this is a pure liquid. Do you see the difference? This would be in, this would be out.
So any aqueous.
Right. They're considering that a pure liquid and a pure solid in any of these reactions, their concentrations are so far greater than the gas or the aqueous ions that they don't matter. Trust me. Okay, KP would be this. Whew. Deep blue solid copper to sulfate penhydrate. Who had this when we did the hydrate lab, when we heated up everything to abnormally high? Yeah, that really blue, pretty blue one?
Yeah.
That was nice. Copper sulfate penhydrate. What was the state of matter of this?
Liquid and solid.
It was a solid. Until the water,
Oh,
Yeah,
okay.
okay,
You were asking-
is heated to drive off
Is that
water
how you-
vapor and form solid white copper to sulfate.
Is that how you denote heated?
Yes.
Interesting.
Solid, okay. Balance. Okay, did. Right, KEQ, okay.
Is that a 3 inch or is that two?
What is that? Oh, no, it's a solid. Okay. That is not you. What did I do there?
What's the
All right.
delta above the?
That means heat. You people are driving me crazy today. Yay?
What is the P on the answer?
That's the partial pressure,
But why is there a P in front of it?
because that's saying that it's the partial pressure equilibrium.
No, to the
No,
right.
No,
Like
the
the
other
huge
side.
P
Oh,
to the
that's
right.
partial pressure of water.
Oh, okay.
I was like, I don't know how much clearly I can say that, but I was going to try.
Well-
Okay, the following equilibrium concentrations. Equilibrium concentration. Who watches that show, The Middle? Have you ever? I don't know why I watch it. I hate that show, but I watch it because that kid is so delightfully different. He talks to his stomach. Have you ever seen
Oh,
that?
wait, is that the one with the unit?
Yeah. Yeah. Okay.
Malcolm in the
Malcolm.
The old.
No. This is. Okay, can we get back to this? Here is an error. This should say 3.1.
Oh my gosh.
The following equilibrium concentrations were observed for the Haber process at 127 degrees C. N2 gas plus 3 H2 gas yields 2 NH3 gas. Here are the equilibrium concentrations at that temperature. Calculate the value of K for this reaction. First, let's write K. KEQ is equal to NH3 over N2 H2. Everybody agree with me there? That's the law of mass action. These are the values that go into. You all right?
I'm gonna take a wild guess. 3.8 times 10 to the 4.
You are a genius. When you do this math, and please be careful of your orders of operation, because your calculator will just do what you tell it to do. Don't tell it to do it incorrectly. It's 3.8 times 10 to the 4th. Okay, in this reaction, when it comes to equilibrium, is there more N2, H2, or is there more NH3?
More NH3.
NH3, okay. Now, it says calculate the value of the equilibrium constant at 127 degrees C for the reaction, which is the reverse, correct?
So it'd be 1 over.
So the reverse reaction would be equal to 1 over the forward reaction, which would be 1 over 3.8 times 10 to the 4th, which should be a very little number, and it is 2.6 times 10 to the negative.
Whenever they give us a picture, is that, will we assume that was constant temperature?
That's
Oh,
it.
it said 127 on the
Yeah,
board.
yeah.
How would you?
Remember, K is temperature dependent, so anytime you talk about an equilibrium expression, the temperature must be mentioned so you know what you're talking about, because the equilibrium concentrations are gonna be different.
But if the temperature doesn't change during the reaction, is there a way to,
Yes,
change
but
the-
you don't have to worry about that, that's
Okay.
beyond the scope of this course.
All right.
Calculate the value of the equilibrium constant at 127C for the reaction given by the equation. What's the difference between this and this?
Not much.
It was divided by 2. So what are you going to do to K?
Divided by 2.
You're going to raise it to the 1/2, right? And you can't, so what is K? Remember, whatever you do to the reaction, you do to the exponent.
So
Yeah. Okay, so K was 3.8 times 10 to the 4th.
Does the temperature matter?
And
like
now
Kelvin?
hang on for a second. I'm going to raise it to the 1/2 power, which you can't fool me. That's like taking the square root. And that gives me this. What's your question?
Does the temperature matter?
Absolutely matters.
I mean, at